In this part of the lesson, we're going to look at problem solving with proportions. We're going to start by talking about direct proportions. The example that Steve just did with the French fry and carrot stick orders at Uncle Jeb's Chicken Hut was an example of a direct proportion. We'll do more problems like this. And then we're going to look at one example which will lead to an inverse or reciprocal proportion. This won't be direct. And we're going to finish up by talking about proportions in geometry. And this will be a nice segue into Candace's part of the lesson, where she'll talk about angle measure in triangles. Let's start with direct proportion. A sports coupe travels 370 miles on 20 gallons of gas. How many miles can it travel on 12 gallons of gas? So this problem can be solved in two ways. We can either calculate a rate, or we can solve the problem using a proportion. So I'm going to start by calculating a rate to find the solution. So to calculate the rate, I basically want to know the fuel consumption rate in miles per gallon. So I'm going to divide 370 miles by 20 gallons of gas. And that will give me miles per gallon. So let's see, 2 goes into 37, let's see, 18 and a half times. So this would be 18.5 miles per gallon. If I multiply 18.5 miles per gallon by the 12 gallons of gas we now have. Now notice the units will cancel. Gallons over gallons is just 1, and we'll be left with miles. So I'm going to multiply 18.5 by 12. So 18.5 times 12, that's 222 miles. So we can conclude that the sports coupe can travel 222 miles on 12 gallons of gas. Now I said that there was two ways to solve this problem. We just used a rate to find the solution. Now let's look at how we could do this using a proportion. So what I have here is a table, and in the table I'm going to put the information into the table that I'm going to need to solve this problem. So I know that when the car drives 370 miles, it uses 20 gallons of gas. And when 12 gallons of gas are used, the question is, how far can the car travel? So I have a table in which I've organized all of my information. Let me move the table out of the way so we have some place to do our work. So there's a couple of different proportions I can write using this table. What I have here is a comparison of rates. I've taken 370 miles per 20 gallons, and I'm comparing it to d miles per 12 gallons. This compares two rates. I can also write two more proportions from the table. I can compare miles to miles. 370 miles to d miles should be the same as 20 gallons to 12 gallons. This is a comparison of two ratios. I could also turn things upside down. D miles is to 370 miles as 12 gallons is to 20 gallons. I can use any of these proportions to solve the problem. So let's do it. I'm going to let D represent the distance in miles the sports coupe drives. And now I'm going to write a proportion. And I think this time I'm going to compare distances to distances. So 370 miles is to d miles, and gallons to gallons, as 20 gallons is to 12 gallons. And now solving this proportion, I can use the cross multiplication trick this would give me 20D equals 370 times 12. And if I divide both sides of this equation by 20, I have 20D over 20 equals 370 times 12 over 20. Now, if you look very closely at what I just have here, this 370 divided by 20, that was the fuel consumption rate. That was the 18.5 miles per gallon times 12 gallons. This is precisely the same calculation we did last time. So we get the solution D equals 222. We stated the conclusion the first time we solved the problem, so I'm just going to leave it like this right now. Let's look at another example. The amount of garbage produced in a city is proportional to its population. A city of 1.5 million people generates 30 million pounds of garbage each week. Estimate the amount of garbage generated each week in New York City, which has a population of 7.5 million people. So here we're told that the amount of garbage produced is proportional to the population size. So we're definitely going to set up a proportion to solve this problem. So we're going to do the same thing. We're going to make a table to organize the information. And we were told that a city of 1.5 million people generated 30 million pounds of garbage. And the question is, New York City, which has 7.5 million people, how many pounds of garbage is generated each week? And I'm just going to put X there because X is our unknown. So now let me define my variable and set up a proportion so that I can solve this problem. So I'm going to let X represent the amount of garbage in millions of pounds generated each week in New York City. And now I want to write a proportion. Now I can compare garbage to people, I can compare two rates, or I can compare garbage to garbage, population to population. I think this time I'll equate two rates. So I have 30 is to 1.5, so the number of pounds of garbage per person, as X is to 7.5. Now let's solve this proportion. So I had 30 is to 1.5 as X is to 7.5. Writing the equivalent equation, 1.5x equals 30 times 7.5. Dividing both sides of this equation by 1.5, 1.5x divided by 1.5 equals 30 times 7.5 over 1.5. And now I want to simplify and get x equals some number. Well, here I think I can do the arithmetic because I know 15 goes into 30 twice, so 1.5 goes into 30 20 times. And 20 times 7.5 is 150. Now remember, X represented the amount of garbage produced in New York each week in millions of pounds, so we can state our conclusion that every week in New York City there is 150 million pounds of garbage produced. Now, one thing I forgot to do was check this solution. And when we're checking a proportion, we can actually just check to make sure that the two ratios are indeed equal. So what I'm going to do is go back to my ratios up here and calculate each one of these ratios using my x equals 150. So I'm first going to divide 30 by 1.5. That's 20. We talked about that already when we were solving the equation. Now I need to check that when x is 150 divided by 7.5, that's 20 as well. So I can see that in my proportion, both ratios are equal, so now I'm confident that my solution is right, and I can move on. Here's another example. Biologists in South Africa tag 150 largemouth yellowfish in a small lake. 1 month later, they netted 72 yellowfish and discovered that 16 of these were tagged. How could biologists use these numbers to estimate the number of yellowfish in the lake? So what the biologists are doing is something called sampling. And the sample of fish netted is a representative sample of the fish in the lake. So let's see what we mean by this. I'm going to fill out the information in the table that we were given in the problem. So we were told that they had tagged 150 of these fish in the lake. So in the lake, we know there's 150 tagged fish. In the sample, they found 16 tagged fish out of 72. So in the sample, 16 out of 72 fish were tagged. If this is a representative sample, that would mean that in the whole lake, things should be proportional. That if we have 16 out of 72 tagged in the sample, then 150 out of the total population of the lake, it should be in the same proportion. So this is what we mean by saying this should be a representative sample. What's in the sample should be proportional to what's really going on in the whole lake. So let's solve this problem. So I'm going to let P represent the population of yellowfish in the lake. And now I'm going to write a proportion. So I think what I'll do is I'll compare the actual numbers in the lake to the numbers in our sample. So 150 is to P as 16 is to 72. And solving this proportion should help us find the total population of fish in the lake. So 150 is to P as 16 is to 72. Writing the equivalent equation, 16P equals 150 times 72. Dividing both sides of this equation by 16, I get P equals, so let me do this computation. I have 150 times 72, and I want to divide that by 16, and I get 675. So before I state a conclusion, let me just make sure that the fractions work out. I need to compare 150 to 675, and that should be the same as 16 to 72. So 150 divided by 675, that gives me 0.2 repeating. And when I calculate 16 divided by 72, I get 0.2 repeating. So indeed, P equals 675 makes these two ratios equivalent. So to state my conclusion, there are 675 fish in the lake based on this representative sample. So this is an estimate, but it is an estimate that the biologist can use. In this part of the lesson, we're going to look at something called inverse proportions. All the proportions we have looked at so far have been one type. We're going to see something that's a little bit different in this example. A crew of 4 takes 12 days to clean up debris after the demolition of a building on campus. How long would it take a crew of 15? Well, how is this different than some of the problems we've looked at before? What's happening here is that we are increasing the crew size. But if you think about how long it's going to take to do the job, when we have more people working the job, we would expect the amount of time on the job to decrease. This is very different than the proportions we've been looking at earlier in today's lesson. So to think about this, let's start by trying a simpler problem. So here's a question we could ask. How long would it take a crew of 8 to clean up the debris? Well, if it takes 4 people 12 days, then we would expect that it would take a crew of 8 only 6 days or half as long to clean up the debris. So how long would it take a 1-person crew? Now this is actually a very important idea. If it takes 4 people 12 days, then we would expect that it would take 1 person 48 days. So I would say that it would take one person 48 days. What we did is we multiplied 4 persons by 12 days to get a unit of 48 person days. Now you might think this is kind of a bizarre unit, but you've probably heard people talking about the amount of man-hours required to do a job. Well, this is just it. It's the same idea, except now we're measuring this work in person days. So how can we use this to answer the question? Remember, our question was, how long is it going to take a crew of 15? Well, if I take my 48 person days and divide that by my 15 person crew, notice what the units of the result is going to be. It's going to be days. That's what I want to know. So pulling out my calculator, 48 divided by 15 is 3.2. So now I can answer the question in the problem. It will take a 15-person crew, 3.2 days to clean up the debris. Now in my calculation, remember I said that person divided by person is 1, so we'd end up with days. So let me just include my units in my computation. So now, there's something about this problem that seems somewhat proportional. We said that it would take a crew of 8 only 6 days. So when the crew size doubles, the amount of time on the job is cut in half. So can we handle this problem somehow as a proportion? So I'm going to create a table just like we did with our proportion problems. And I'm going to define a variable here from the unknown. So I'm going to let t represent the amount of time it takes to clean up the debris in days. So we were told that a crew of 4 takes 12 days, and we want to know how long it's going to take a crew of 15. So what we've been doing in previous examples is we've been writing proportions using our tables. But here something different is going on, so we have to be a bit careful. For example, what's wrong with this proportion? We said before that the amount of time that it will take 15 people to do the job, that's t, should be less than the amount of time it takes for 4 people. So in this situation, the denominator will be less than the numerator, which isn't going to work with this proportion. So can we somehow use a proportion to solve this problem? Well, let's go back to our idea of person days. What we saw earlier is that 4 persons times 12 days, that was our 48 person days, and we want this to equal 15 persons times t days. Well, let's think of a proportion we could write that would lead us to this. So we could write 4 is to 15 as t is to 12. If I cross multiply, 4 times 12 equals 15 times t. The proportion we had written before had the reciprocal of t over 12. Sometimes these types of proportions are called reciprocal proportions, and they are indeed a little bit trickier to work through. So now let's write our conclusion. It will take a crew of 15, 3.2 days to clean the debris. So before we finish this, let's just say something about these inverse or reciprocal proportions. So here's a direct proportion. This is what we've been working with in previous examples in this lesson. Two quantities A and B are in direct proportion if the ratio A to B is constant. What's happening with inverse or reciprocal proportions? Two quantities A and B are in inverse proportion if the product AB is constant. This probably sounds a little bit abstract, so let's go back to our demolition example. As the number of workers on the crew doubled, the number of days needed to complete the job was halved. 2 times 1/2 is a constant, 1. This last example was an example of an inverse or reciprocal proportion. Sometimes they do occur, and we have to work with them very carefully. So let's finish things up by looking at some proportions in geometry. Although all rectangles share many properties, not all rectangles have the same proportions. So we have a picture here of 3 very different looking rectangles. 2 rectangles are proportional if the ratio of their corresponding sides is equal. So let me show you an example of 2 proportional rectangles. Here's one rectangle, and if I blow it up by a constant factor, I get a proportional rectangle. You can see these 2 rectangles have the same shape in the sense that they are proportional. So if I label the width and the length of the small rectangle using lowercase letters and the large rectangle using uppercase letters, these 2 rectangles are a proportion if the ratio of W to L equals the ratio of capital W to capital L. That's what we mean by proportional rectangles. Now, all circles are proportional because the ratio of a circle's circumference to its diameter is the same for every circle. So here's a little circle. Its circumference is just the distance around the circle. Its diameter is the distance across the circle, the distance measured through the center. And when I look at the ratio of the circumference to the diameter, it equals pi. This is where the number pi comes from. And if I take a bigger circle and measure its circumference and measure its diameter very, very carefully, the ratio of the circumference to the diameter will be pi. All circles kind of look the same because they're all proportional. 2 triangles are proportional if the ratio of their corresponding sides are equal. Proportional triangles are similar triangles. So here's one triangle. If I compress it in a proportional way, I get a second triangle, which is proportional. So if I look at the ratio of this side to this shorter side, it should be the same as the ratio of this horizontal side to this horizontal side. That's what we mean by similar triangles. Now, the triangle shown in this figure is a right triangle. And right triangles have one 90-degree angle or a right angle. So we usually designate that with a little box. The 2 sides of the triangle that contain the right angle are called the legs of the right triangle. Here are the legs. The side opposite the right angle is called the hypotenuse. So when we use right triangles in applications, we often talk about legs and hypotenuse. And a figure that emerges in the context of some applications shows similar right triangles sharing an angle. So here's one right triangle, and here's a proportional right triangle, and they share this angle down here. Now this picture might show up in the application in a different orientation. For example, when you draw a figure to help you solve the problem, the two similar triangles might look like this. And in fact, depending on the problem, this picture could have all sorts of orientations. But we need to recognize that what we have here are just two proportional right triangles. So let's use right triangles to solve a problem. Jordy and his mates decide to measure the height of a totem pole recently installed in a park downtown. They bring a 1-meter stick, a measuring tape, and plenty of sun. They determine that the length of the shadow cast by the totem pole is 22.5 meters. Jordy positions the 1-meter stick so that the shadow it casts ends at the same point that the shadow cast by the totem pole ends. Jordy's mate Amy determines that the meter stick casts a shadow that is 2.25 meters. How tall is the totem pole? So what we're going to do first is draw a figure to get a picture of this. So I'm going to start by drawing my totem pole, and it's not going to look like a totem pole. It's going to look like a vertical straight line. And what the totem pole is doing is it's casting a shadow on the ground. So here is the totem pole, and here is the shadow. And the shadow was 22.5 meters. And I'm going to draw a right triangle here. Because it's the sun that's living out here somewhere that's causing this shadow. So now what Jordy and his friends did is they put a 1-meter stick so that the shadow cast by the 1-meter stick ends at exactly the same place as the shadow cast by the totem pole. So this distance is 1 meter, and this shadow here was 2.25 meters. Now, in these similar triangles, the ratio of sides are equal. So what I'm going to do is define a variable and set up a proportion. So I'm going to let h represent the height of the totem pole, and I'm measuring in meters. So this is h in my picture. And so what I know is that the short leg of the right triangle in the big triangle is to the short leg of the right triangle in the smaller triangle as these longer legs are to one another. So that would be as 22.5 is to 2.25. And this actually is very simple to solve because I noticed 22.5 is the same as 2.25 with just the decimal place moved over 1. So I get h equals 10. So this tells me that the totem pole is 10 meters tall. So let me state that conclusion. The totem pole is 10 meters tall. So see what you can do with just a little bit of sunshine and a lot of geometry. So I'm going to turn this over to Candace, who's going to talk a lot more about triangles.
In this part of the lesson, I'm going to talk about angle measure. First, I'm going to talk about the angles of a triangle and do some examples. And then I'm going to talk about complementary and supplementary angles. Let's start by looking at the angles of a triangle. The sum of the measures of the angles of every triangle is 180 degrees. In this triangle, I have two angles with a measure of 70 degrees and one angle with a measure of 40 degrees. If we add these up, we get 180 degrees. This type of triangle is called an isosceles triangle because two of the angles have the same measure. In this triangle, I know that I have a right triangle because of the square at the bottom. This is indicating a 90-degree angle. If I add up the two smaller angles, 68 degrees and 22 degrees, I get 90 degrees. That added to the 90-degree right angle is 180 degrees. Look at this triangle. What would be the measure of the side, or excuse me, the angle that's not labeled? I have two angles labeled 80 degrees and 58 degrees. If I add up 80 and 58, I get 138. I would need to add 42 to that to get 180 degrees. So this missing angle must be 42 degrees. An equilateral triangle is a triangle with three equal sides. Here's an example of an equilateral triangle. Here's another example of an equilateral triangle. Well, if all three sides of a triangle are equal, the angles of the triangle have to be the same as well. What is the measure of an angle of an equilateral triangle? Well, if all three sides have the same length and all three angles are the same, I can label each of these angles as x. So let me define my variable. I'm going to let x represent the measure, and this is in degrees, of an angle in an equilateral triangle. So we know that the sum of the measures of all three angles has to be 180 degrees. So if I add x and x and x, this is going to have to be 180. So my equation simplifies to 3x equals 180. And if I divide both sides of the equation by 3, I think I can do that in my head, 180 divided by 3 is 60. 60 plus 60 plus 60 is indeed 180. So that checks, and I can say the measure of an angle in an equilateral triangle is 60 degrees. Let's look at another example. This time we're told that the largest angle of a triangle is twice as large as the smallest. The measure of the third angle is 20 degrees less than the largest angle. Find the measure of each angle. So I think here it would be very helpful to draw a picture. So let's draw a triangle. So it looks like this is probably my largest angle. I'm going to think of this as my largest angle. A little bit hard to tell, but let's say that this is my smallest angle. I'm going to use my variable to represent the smallest angle. So I'm going to label this angle y, because I'm told the largest angle is twice as large as the smallest. So if y is the smallest angle, then my largest angle needs to be 2 times y, twice as large as the smallest. And I'm told the third angle is 20 degrees less than the largest angle. So my third angle over here needs to be 20 degrees less than 2y. So 2y minus, because it says less, 20. Well, now I want to make sure that I define my variables. I drew them on my picture, but I want to have a clear definition. So on my picture, I let y represent the smallest angle. So let y represent the measure in degrees of the smallest angle. then 2y, our largest angle, and 2y minus 20 represent the measures, also in degrees, of the other two angles of the triangle. Well, the next thing I'm going to want to do is write an equation. Here I need to think again about the fact that the measures of all of the angles of a triangle add up to 180 degrees. So my angles are y, 2y, and 2y minus 20. So if I add y and 2y minus 20, this needs to sum up to 180. Combining my like terms, I have y plus 2y is 5y minus 20 equals 180. Now if I add 20 to both sides of the equation, 5y minus 20 plus 20 equals 180 plus 20. That gives me 5y equals 200. And if I divide both sides of the equation by 5, this gives me the equivalent equation, y equals 40. Now y was my smallest angle of the triangle, so the measure of the smallest angle of the triangle, it looks like is going to be 40. I want to check this in the context of the problem and make sure that this actually does make sense. So if my smallest angle is 40 degrees, the largest angle is twice that. The largest angle would be 80 degrees. And the third angle is 20 degrees less than the largest angle. So the third angle would be 60 degrees. If I add these up, 40 and 60 is 100, plus 80 is 180. This is precisely what I wanted. The sum of the measures of the angles adds up to 180 degrees. So this triangle makes sense. So I can go ahead and write my conclusion. The measures of the angles of the triangle are 40 degrees, 60 degrees, and 80 degrees. Let's look at another application. This time we're told two angles of a triangle have the same measure, and the third angle is 30 degrees more than the other two. Find the measure of each angle. Well, this time, since I'm told two angles of the triangle have the same measure, I know I'm dealing with an isosceles triangle. So let's see if I can draw an isosceles triangle. Close enough. So I'm going to assume that these are the two angles that have the same measure. I'm going to label those M. And I'm told the third angle is 30 degrees more than the other two. More than makes me think add, so I need to add 30 degrees to M. So this angle I'm going to label as M plus 30. Now I want to make sure that I define my variables, even though I've written them on the diagram. So I'm going to say let M represent the measure, and this is measured in degrees, of one of the equal angles in the triangle. And then I can say M plus 30 represents the measure of the third angle. And this is also going to be measured in degrees. Now I want to write an equation. Again, I'm going to use the fact that the sum of the measures of the three angles should be 180 degrees. So I'm going to add m, and m plus 30. So my equation is m plus m plus m plus 30 equals 180. Combining my like terms, I have 3m plus 30 equals 180. Now I'm going to subtract 30 from both sides of my equation, which gives me 3m equals 150. Finally, I'm going to divide both sides of the equation by 3. And this gives me m equals 50. Now, before writing my conclusion, I want to make sure that this makes sense in the context of this problem. So the m is the measure of one of my equal angles of the triangle. So I actually have two angles whose measure is 50 degrees. The third angle is supposed to be 30 degrees more than the other two. So 50 and 30 is 80. And if I add these three angles together, 50 degrees plus 50 degrees is 100, plus 80 degrees is 180 degrees. And this checks. The sum of the measures of every triangle should be 180 degrees. So I can say, for my conclusion, the measures of the angles of the triangle are 50 degrees, 50 degrees, and 80 degrees. Now I want to look at something we call complementary angles. So let's start with the definition. Two angles are complementary if the sum of their measures is 90 degrees. So if we had a 62-degree angle and a 28-degree angle, since 62 plus 28 is 90, these two angles are complementary angles. Let's look at an example. Two angles are complementary. One angle is 15 degrees less than twice the first angle. What are the measures of the two angles? So let me start with a picture here. So I know I have two complementary angles. The sum is going to be 90 degrees. So I'm going to start with a right angle, a 90-degree angle. And I'm going to break that up into two pieces for my two complementary angles. One angle is 15 degrees less than twice the first angle. So if I label this as my first angle, I'm going to call it C. Then the other angle is 15 degrees less than twice this one. Twice this one means 2 times this one. So 2C. 15 degrees less means I'm going to subtract 15. So 2C minus 15. Now I'm going to clearly define my variables. So I'm going to let C represent the measure. In degrees of one of the complementary angles. Then 2C minus 15 represents the measure, also in degrees, of the other angle. Now this time when I think about writing my equation, I have to remember these are complementary angles. The definition of complementary angles is that the sum of complementary angles is 90 degrees. So when I add C and 2C minus 15, I should get 90 degrees. So my equation should be C plus 2c minus 15 equals 90. Now combining like terms, I have 3c minus 15 equals 90. Now I'm going to add 15 to both sides of the equation. This gives me 3c equals 105. So to isolate c, I'm going to divide both sides of the equation by 3. And this gives me c equals 35. Now before I write my conclusion, I want to make sure that this makes sense in the context of the problem. So for my check, well, I know that I just solved for c and found c is 35. My complementary angle to that was 2c minus 15. So if c is 35, then 2c minus 15 is 2 times 35 minus 15. 2 times 35 is 70. If I subtract 15 from 70, I get 55. So how does my check work? Well, these angles are supposed to be complementary. What happens when I add 35 degrees and 55 degrees? I get 90 degrees, precisely the definition of complementary angles. So now I can state my conclusion. The measures of the complementary angles are 35 degrees and 55 degrees. Let's look at another application. A totem pole casts a shadow on the ground. The angle of elevation from the ground to the line of sight to the top of the totem pole is 30 degrees. What is the measure of the angle denoted by A in the diagram? So in the diagram we see our totem pole. The line at the bottom represents the shadow the totem pole is casting. We see our 30-degree angle of elevation. We see our angle A, but we also see an angle labeled B in the diagram. So let's get rid of the totem pole and look at the triangle that we can use for this diagram. I can see that I have a right triangle. The totem pole and the ground create a right angle. So this angle has a measure of 90 degrees. I'm also given this 30-degree angle. So the angle B, when I add that to the 30-degree angle and the 90-degree angle, must make this add up to 180 degrees. Well, if I have a 90-degree angle and a 30-degree angle, that's 120. So B must be 60 degrees. But I wasn't asked what B was. I was asked about the measure of angle A. The next thing I need to note here then is I have another right angle in this diagram. A and B are complementary angles. Well, since we just found that B had to be 60 degrees, then the measure of angle A is going to have to be 30 degrees. There we have our complementary angles forming 90 degrees, forming a right angle. So the measure of angle A is 30 degrees. An angle of measure less than 90 degrees is called an acute angle. Right triangles have 2 acute angles and 1 right angle. When we looked at our totem pole diagram, we had a right triangle. The 2 smaller angles had measures 30 degrees and 60 degrees. 30 plus 60 is 90 degrees. The acute angles of a right triangle are complementary. So in our example, we had a 30-degree and a 60-degree angle, but it doesn't matter what the measures of these 2 acute angles are, they're always going to add up to 90 degrees. Since we have a right angle, which is 90 degrees, adding 90 degrees to that gives us 180. The sum of the measures of the angles in every triangle is 180 degrees. So the sum of the 2 acute angles must be 90 degrees, which means the 2 acute angles of a right triangle are complementary. Well, now let's look at supplementary angles. Starting with a definition, two angles are supplementary if the sum of their measures is 180 degrees. A line forms an angle that measures 180 degrees. Here's a 180-degree angle. If I had a 62-degree angle and a 118-degree angle lying on this line, 62 plus 118 is 180. So these are called supplementary angles. Let's look at an application with supplementary angles. A steel beam is to be welded to a cross beam, creating two angles. If the outer angle is to be 15 degrees less than twice the inner angle, what are the angle measurements? Well, it might be a good idea to have a picture of what's going on here. So here I have a picture of a cross beam. Actually, I have two cross beams and 6 steel beams. You might think of this as some kind of a support system. You might have seen this when a building was being constructed, or you might have seen some kind of a support system like this in a bridge. In this problem, we're just focusing on one cross beam and one steel beam. We're told the outer angle is 15 degrees less than twice the inner angle. So if I label my inner angle with the variable b, then my outer angle is to be 15 degrees less than twice the inner angle. Well, twice the inner angle means 2 times b, so that's 2b. 15 degrees less means I need to subtract 15. So my outer angle would be 2b minus 15. So in my picture, I had b for my inner angle and 2b minus 15 for my outer angle. Let me define my variables. So let b represent the measure, and we're measuring in degrees, of the inner angle. Then 2b minus 15 represents the measure. This is also measured in degrees of the outer angle. Well, how am I going to write an equation to help me solve this problem? What I have to use is the fact that these two angles are supplementary angles. So the sum of the measures of these two angles should be 180 degrees. When I add b and 2b minus 15, I should get 180. So if I add b and 2b minus 15, I should have 180. Combining my like terms, b plus 2b is 3b, so 3b minus 15 equals 180. Now if I add 15 to both sides of the equation, that leaves me with 3b equals 195. If I divide both sides of the equation by 3, 3 goes into 195 65 times. So let's see if this makes sense. If my inner angle, b, is 65, then my outer angle, 2b minus 15, would be 2 times 65 minus 15. 2 times 65 is 130. 130 minus 15 is 115. So what's my check? Well, these have to be supplementary angles. The sum of 65 degrees and 115 degrees is indeed 180 degrees. So this checks. So I can go ahead and write my conclusion. We were asked for the angle measurements for these angles created by the crossbeam and the steel beam. So the angle measurements are 65 degrees and 115 degrees. And that concludes today's lesson on proportion, ratios, and geometry.